Thank you for the introduction. First of all, I'd like to thank to the organizers inviting me to the wonderful conference and beautiful place. And today, I talk about mainly I talk about the models of Motzkin chain model because that yesterday and previous Pram talk Fumihiko model that talked too much. This is a literature to the Motzkin models, and also we discuss about Renyi entropy of the Motzkin models. So this is one of the result of this paper with Professor Bradley Colvin. Okay, so that outline. So that these two review of the Motzkin models, colorless model and the colored models, and then we discuss the Renyi entropy of this model. So okay, first let me begin with the quantum entanglement. That quantum entanglement is the most surprising feature of quantum mechanics that no analog of quantum mechanics. And this feature is crucial to quantum computation. And so what is this? Okay, so let's start with the pure state on the full system. This is a pure density matrix of pure state, and we get the reduced density matrix. Okay, we pick some subsystem A in this full system. Then we trace over the other remaining environment. Trace over with respect to the other remaining environment. Then we get the reduced density matrix of rho A. Then the rho A can become mixed states in general. Then we have a non-zero entanglement entropy. This is the definition of the entanglement entropy. That's this purely quantum property. Okay, and okay. So entanglement entropy. We discussed area law. So area law is that already discussed yesterday for sure Katsu's talk. And in general, ground set of quantum many-body systems with having a local interaction that exhibit the area law behavior in the entanglement. That's entanglement entropy proportional to the area of subsystem A, a boundary of a subsystem A. For gapped case, one-dimensional gapped case, the system, the entanglement entropy satisfied to area law. That's proven by Hastings. But the gapless case, for example, 1 plus 1 dimensional conformal field theory violates the area law logarithmically like this. So to see the central charge of the conformal field theory. So these properties are discussed with before. Okay, so recently there are discovery of interesting models and one-dimensional solvable spin models. That model exhibits very large, big entanglement entropy. That entropy is violates logarithmic that entropy violates more than logarithmic violation. It's the square root of a volume. So this kind of model, I have there are two kinds of these models. So one is the Motzkin model, that is Showa model, and also the other is the Fredkin model. Okay, and next we discussed Renyi entropy. So Renyi entropy, this is the definition of Renyi entropy. So this quantity has parameter alpha, continuous parameter alpha. Alpha is a positive real number, but not one. So this quantity has a continuous parameter. So because of this, the quantity has further importance in the von Neumann type entanglement. Also, this quantity, the generalization of the von Neumann type entanglement. Because in the limit of alpha goes to 1, this quantity reduces to von Neumann type entropy. And also, once we know that this quantity as a function of alpha, we can reconstruct a full spectrum reduced density matrix or entanglement Hamiltonian that given by this given by this. Also, one-dimensional gap case. Also, this Renyi entropy proven to obey area law by Huang. So in this lecture, I give mainly I give about Motzkin spin chain model and computation of the Renyi entropy of half chain. Okay, so let's continue to Motzkin spin case. Yeah. Okay, so we consider that the one-dimensional spin chain as size is 1 to 2n. So the size is 2n. Then we put spin one state in the each side. So up and down and 0. This is spin. And associating with this state, we can regard the steps in the 2D planes, up step and down step at flat steps. Yeah. This is also as I introduced that yesterday and Pramod talked today. So this correspondence, so each spin configuration to map to length 2 invoke in xy two-dimensional plane. This is the example, length 6 case. So this is a spin configuration, up 0, down, up, down. So we can draw this kind of work. Okay, then we introduce the Hamiltonian over Motzkin spin model. This is a colorless case first. This is a bulk part. Bulk part consists of sum of projection operator. This is a projection operator acting on a spin, side j and j plus 1. So this is a nearest neighbor interaction. Then state D is, this is the definition of state D. So this is first side is 0 and the second side is D. And the up state is also 0 and U and myself U and D, and so on. So associated with this state, we consider the zero energy state. So that orthogonal to these states. So we consider like this. So we consider the orthogonal state. So the 0D plus D0 we consider. So this case is for corresponds to the path. If we find this path, we should also have this path. Yeah, this is equal weight superposition. So in this case, in this situation, we write by using this symbols, the equivalent symbols. Also, in this case, also this is a flat up and up flat equivalence, and this is flat flat and up and down. This is okay. So that's the bulk part. This is a boundary Hamiltonian boundary part. This is the left boundary is DD and right boundary is UU. So this means to obtain a zero energy state, left boundary should be flat or up, and the right boundary should be flat or down. Okay. So So this Hamiltonian, the sum of the projection operators, that the spectrum is positive semi-definite. And actually, we find the unique zero energy ground state. Yeah, this is, state is So the zero energy state is the ground state. And that we actually find a unique ground state. Yes. So each projection of the Hamiltonian analyzes this ground state. So this property is called the frustration. And yes, and with the correspondence to the path, the ground state can be regarded as starting at the origin and ending at the 2n comma 0, but restricted to the region as region in the y, the non-negative region of the y. So random walk satisfying these properties called the Motzkin walks. Also, we can rewrite that spin S equal 1 spin matrices. We can rewrite the Hamiltonian in terms of S equal 1 spin matrices. This is like this. So this is the nearest neighbor chaotic spin interactions. Okay. So this is an example of a ground state. It's length 4 case. This is a ground state. 0, 0, UD, blah, 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 blah. So the corresponding Motzkin walk is like this. So the normalization factor 9 appearing in normalization factor. This 9 is the number of this state. So number of the Motzkin walks. Then, yeah, there's some notes. So this Motzkin path is a forbidden, something, there are some forbidden passes. So in this Hamiltonian, how realize this forbidden passes? If you consider that a length 4 pass and entering a y negative region, like this pass. But using an equivalence relation, we get this pass. But this step is forbidden by a boundary Hamiltonians. Yeah. So left boundary is flat to up. So forbidden. Also at the path ending at the non-zero height, if we consider this path, so using an equivalence relation, we have this, and also we have this, and we have this. So this path is forbidden. Similarly. Okay. And yeah, so in order to compute entanglement entropy of a subsystem, so we take a left half chain A, 1 to n. So we've computed the normalization factor of the ground state. This is called P to n. This is the state corresponding to 2n passes, length 2n passes. So that normalization factor is given by the number of Motzkin walk of length 2n. So this number is given by this equation. So CK is a Catalan number. Okay. Okay. So now we divide the state 2Pn to state belonging to Hilbert space A and the state of complement of Hilbert space complement to A. So this is like this. So here is the state belonging to a subsystem A, and here is the complement of the Hilbert space of complement. So the complement is I call it B in plus 1 to n. So this is we like decomposition. This type of decomposition is called the symmetric decomposition. So this path, so corresponding state, this path is a path from origin to n to h. So h is the height of a middle. And yes, analogously, this is a path from nh to 2n0. What is this factor? So this denominator, this number is here, and this 2nh factor is the number of this path. So we should compute this number. Okay. So this number is we can compute asymptotic form of this number. We can compute into the infinity. We get this Gaussian distribution like this. So then tracing over the subsystem B, we get reduced density matrix. So this density matrix is diagonal. So this and this are the same, same vector. So this is the diagonal. So the entanglement will be expressed like this. Then we get this logarithmic behavior here. This is uncolored case. Then okay. So this logarithmic violation system is the critical gap. So entanglement entropy is similar to the that of the 1 plus 1 dimensional conformal field theory. The central charge is 3/2. But this system known as the gap scale as 1 over n to z. Z is greater than or equal to 2. So that fact means that this system cannot be described by relativistic conformal field theory. Because the relativistic CFT is a scale as 1 over n. This is different. And also, there are some computational correlation function, Motzkin. There are some computational function, 1 point or 2 point function. but this system is difficult to find, difficult to analyze the excitation. Yeah, so the excitation have not been much investigated. This is the uncolored case. Okay, then we use the colored Motzkin case. So colored case, we introduce color degrees of freedom. This is 1 to S, yeah, to up and down spins. So we have k kinds of up states or k kinds of down states. So these correspond to up step is k kinds of up states and k kinds of down states. So the Hamiltonian is again sum of bulk and boundary part. So bulk part consists of also local interactions as well. So first, and also this is sum of projection operators. So first projection operator is analogous to the colorless case. Just sum of color degrees of freedom. Yeah. This dk, uk, fk, that like this. Yeah, this is already introduced the Plamont talk. Also, we have a cross in projection operator. Here is this is k and k prime is different. So this up with some color and down with so down as a down any other colors that cost the energy. So this means that a color should be matched in up and down pairs for getting a zero energy state. Also, boundary part is analogous to colorless case. So this found that this Hamiltonian has still a unique ground state with zero energy. In spite of introducing color degrees of freedom. This is an example of length 4 case. This is ground state. Yes. This figure is that corresponding color to Motzkin works. Like this. Yeah. Like this. Then KK is should be matched. This up and down should be matched. This is KK and K prime, K prime. So each of K and K prime is matched. Like this. And also again, this number is a number of number of states or number of Motzkin works. So similar to the colorless case, we consider that divide the system to divided by a middle and. The left part is called subsystem A, and the right part is subsystem B. So pass from to origin to n comma h. So this is the Pn 0 to h. This is this pass has h are matched up steps. So okay, so let's introduce that tilted pass. Tilted pass means that the pass with the colors of a matched up step is frozen to some color degrees of freedom. So I call that matched up from height m minus 1 to m is I call that u kappa m. The kappa m is frozen meanwhile. Also similarly, h to 0 step, h to 0 pass is a tilted pass. Also that frozen to down. So that the number of tilted pass is related to by this equation. So because of because the pass is frozen or unfrozen. This is an example that length 8 pass and height is 2 case. So this pass. So this pass apart belonging to subsystem A is like this. Yeah. So this so this up and down pair is matched, but this pass and this pass is matched as long as considering only in the part of A. So this pass is eventually we consider whole pass. This kappa 1 pass, this up step is matched to down step here, and up step is kappa 2 is matched to here, like this. Okay. So we get yes, introducing this tilted pass, we can write ground state as a following decompositions like this. Yeah. So this so this is yeah, this state is belonging to subsystem A. This is belonging to subsystem B. This is a frozen path, but eventually we sum over a frozen path. So this yes, this probability factor PNNH is written. So this is a number of tilted paths. Then again, BBT similar computation. This is a reduced density matrix. Again, this is diagonal. But the difference is that yes, this kappa 1 to kappa 8, these dimensions are different compared to color case. Okay. So this case, yes, we find that asymptotic behavior like this. The main, yeah, the difference is the main S to the minus S factor, the S to the minus H factor. This is the main difference. So we compute the entanglement to be like this. So this S to H factor comes from a sum over this, yeah, this sums. Yeah, because of P, because of P and H is independent of kappa. Yeah, kappas. Yeah. So we get this factor. So in this, yes, in this expression, P is this behavior. So this S to H is cancelled with this one. Yeah. So for this expression, we have a Gaussian yeah, distribution, and times logarithm. But the logarithm is very small. So this Gaussian factor, we can regard that this sum in the effectively the height is contribute to at most square root n. So yes, yeah. So using this factor, yeah, we can get this factor, yeah, like this. So this is the S dependent factor. This is the square root growing. So there are some comments. So color case, we have a matching the color. So matching color gives to S to minus H factor in this probability factor. So this factor is crucial to order square root and behavior entanglement. Okay. So as discussed yesterday, also for spin 1/2 chain case, only up and down, no flat, yeah, flat or zero spin. Yes, yeah. They are considered a similar model in the behavior of a square root, yeah, square root entanglement. This is a plotting model. And yes, so this model that computed the correlation function in the this paper, and so here we write that the collected 2-point function at the edge. This is spin at the left edge and the spin at the right edge. But the n goes to infinity, we get non-zero connected correlations for s equal larger than 1. So this means that the violation of cluster decomposition property. Yeah, this is the infinitely far away operators, some correlations. But this is due to yeah, strong correlation, yes, because of color matching. Also, as discussed yesterday, so deformation the model achieve more large volume of behavior. Yes. So this case is weighted to most schematic works. It's realized. Okay. So okay, next let's move on to the Renyi entropy computation of the Motzkin model. So what is computed the asymptotic behavior of these expressions? Okay. So colorless case is just using a formula of Gaussian distribution. We get yeah, this is an easy computation. This is the logarithmic growth. Yes, the logarithmic growth, and reduced to Von-Neumann type entropy by taking alpha goes to 1 unit. And yeah, this type of computation is yeah, yes, Motzkin, he already computed at this type of entanglement entropy in the more general length of subsystem A. So by considering a half-chain case, this result is okay. Let's consider the colored case. This is not computed before our work. So previously I liked this one, but yeah, but this formula is valid for H is at most the square root n case. Yeah. If we have H more than that, this formula should have corrections. So okay, so we consider that sum and over Renyi entropy. I mean this sum. Sum and over this. Yes, this sum has this factor. SH, yes, here SH and this factor combine this factor. So okay, so for alpha between 0 and 1, this factor is exponentially growing. Yeah, for current S greater than 1. Yeah. So we compute the saddle point of this sum. That's the order of n. So so this is only valid for scale of n. So so we should go we should reconsider that these asymptotic forms. Yes, we need more careful treatment for asymptotic of P and H. So let's go back to the original expression like this. This is the original expression. Yeah, this is the tilted M and H is the sum over this, and this C is written like this. And M2N is obtained by setting H equal 1 or N to 2N in this quantity. Okay, and now we have asymptotic form of this. First, we consider that the n row this quantity is much greater than 1. I mean, yes, this factorial factor, all the factorial factor is very big. Then yes, this case, yes, consider this case, and this sum evaluated by saddle point method. Then we get this result. So that the row 0 is saddle point value, saddle point value of row up to order 1 term. Like this. So notice that here I don't assume that how much is H? How much is the H? H is the square root, or H is more or less. I don't assume that here. So this formula is valid for all the cases. Actually, from this case, we can take we can use this expression to the previous one. For the H at most is the square root in case. This is the previous expression. So getting this expression, we get some. Yes, this is a complicated looking. So this this quantity n to 2n over rho 0 to 2n, or this factor. So this factor this factor becomes like this in this situation. So these two exponential factors are combined to this Gaussian distribution. We can okay. So first we consider that Renyi entropy for alpha between 0 to 1. So we computed this sum with the use of this expression. So so we do the saddle point analysis, and finally we get this result. So this C is an independent constant factor. Here is n linear terms and also logarithmic terms. yeah, so yeah, sigma is some yeah factor. I wrote somewhere. Yeah, this is sigma. Okay. Yes. So, okay. So in this analysis, we find the saddle point. Saddle point is the order of n, actually order of n, like this. And yes, this is a linear growth. And yes, we also computed the Reyni entropy for Fredkin case. Then we get the same identical log n behavior. Yeah. This is also a linear growth that the subleading term is identical, same. So this is, we expect some universal linear. Okay, this is the explicit form of constant factor. That's complicated, but yeah, that's something like this is alpha equals 0 singular term. This is the logarithmic singularity. Actually, this term is identical with the colorless case. So in this expression, yeah, the different from a colorless case, in this expression, the alpha goes to 1 or s goes to 1 that does not commute with the n infinity limit. So we cannot, yes, we cannot take s goes to 1 or alpha goes to 1 limit in this expression, because this saddle point value is order n, but s goes to 1 or alpha goes to 1 limit, this leading term vanishes. So does the n goes to infinity or s or alpha goes to infinity, that yeah, doesn't commute. Okay. So next, we consider the Reyni entropy alpha greater than 1. So alpha greater than 1 case, before we consider the factor, but this factor now that exponentially decay, not go. So this exponential decay means that the sum, yeah, the h contributed sum is yeah, almost to the order 1. Yeah, less than yeah, at most order 1, h is the dominantly contributed to the sum. So we computed yes, this one is with the use of Gaussian distribution type, Gaussian distribution, OP. Okay, but we have further simplification because this Gaussian term is now is the h is at most order 1. So this type is 1 plus order 1 by n. So this is the further simplification occurs here. Then finally we get this is the expression. Yeah. So this is the first leading term is the logarithmic growth, and this is the finite term. The last term where phi is the mean that this quantity is Rayleigh transcendent. Yeah, this factor. Yeah. So this is the result. So first term is the logarithmic growth. Yeah. Yes. Again, yeah, we computed the Fredkin case. Yeah, this is identical to the Fredkin case. Same. And so this is also same that alpha equal 1 or s equal 1 it does not commute. It's yeah, large volume. So we see that the phase transitions in this. So Reyni entropy grows as order n for alpha is between 0 and 1, but but whereas order log n behavior for alpha greater than 1. So that no analytic behavior happens at alpha equal 1. So this means a phase transition. And okay, so let me let's see that more phase transition. So in terms of entanglement Hamiltonian, we can write this trace A rho A alpha like this. So this quantity is like a canonical partition function. That the alpha is analogous to inverse temperature. In this case, alpha between 0 and 1 is correspond to high temperature, and alpha greater than 1 is a low temperature. So as we saw that the saddle point analysis, this high temperature case is height of a dominant path is order n. Height is order n. But whereas the low temperature case, height of the dominant path is order 1, almost order 1. So this is we can draw the phase diagram like this. So the 1 over alpha is the corresponding temperature. Here is the high temperature phase. It's the Renyi entropy as order n. And low temperature case, Renyi entropy order logarithm of n. Then alpha equal 1, we write that the von Neumann type entanglement. Yes. Yeah, this is analogous to temperature. Yeah. Not real temperature. Yeah. This is something about This is we could it is analogous. Yeah. Temperature. Yeah. Yeah. Yeah, if we regard that the alpha is some coupling constant, that no analytic behavior of alpha, then so okay, so I drew H. H is that this is height over dominant path, like this. Okay. So let's summarize on this discussion. So first, we have reviewed that colored or colorless Motzkin spin models. That model is a big entanglement entropy proportional to the square root of the volume. And next part, we have analytically computed the Renyi entropy of half chain of Motzkin models. Then we find that the phase function at alpha equal to 1, that totally a new phase function. Actually, we see that we saw that the other spin model. Actually, we looked at the result of Renyi entropy of other spin models, other spin chain models, but there are no such kind of phase function. This is a new. And yes, so that alpha between 0 and 1, this is the high temperature, is the behaves as order n, volume rho, and alpha greater than 1, this is the low temperature case, and that alpha is grows to a logarithmic form. Okay. So we also have a similar result of Fredkin spin chain case. So this is the explicit formula of a Fredkin spin chain model. This is the alpha between 0 and 1, we get this formula. So theta is given by this form. So this is a volume rho behavior, and the second term is a logarithmic. And the other is a constant term. This is also same as alpha equals 0 similarity. This is the same as Motzkin case. Then alpha greater than 1 case, we have this expression. This is the logarithmic behavior. But the Fredkin case is this is a constant term is not so universal because the n equal even or odd, we get different behavior. So we have some future directions. So we can considering a Renyi entropy of chain over general length. So we have a conjecture that we will find the same phase function of, for chain of general length. So this is alpha is between 0 and 1 in the volume, and alpha greater than 1 in the logarithm. We expect that happen for general. So, okay, also a similar computation, we can do that semi-group extensions. The semi-group is, this is the topics in the previous talk by Kramot. And also, this is there are any quantum field theory interpretation of these models. In particular, this color traces. Also, that something like holography or quantum gravity application. because this spin chain is a very big entanglement, there are some, yeah, they are interesting to consider some extensions. Okay, so this, thank you very much.